Recorded is rolling. It is Friday, September 5th. You guys have your quizzes back in your folder. Actually, all the assignments from last night, I was able to get them all in your folder. So everything's returned. Now, here's the quiz corrections for partial credit back policy. If you missed any questions, then on a separate page of paper, show how you get the correct answer. So in this class, there are a lot of equation-based questions. So if you can solve something with an equation, then correctly solve the equation. There are a lot of graphs in this class. So if it's a graph, you can draw the graph. Every once in a while, there's a conceptual question like, what's the basis I use for math? In that case, you can just write out the answers. Okay. Yeah.
That is right next to the answer.
I prefer on a separate page of paper. Or if it's on the same page, then I mean, at least a different ink color, make it really obvious, right? But yeah, better on a separate page, so I know what's going on. Oh, okay, here's what you did on the quiz, and here's how you're correcting that. Make more sense, right? All right, so yeah. Let's see. Yeah, that one you can just write. So there's okay. Yeah, like that. All right. All right. So yeah. Show me that you know how to get to the correct answer. I'll give you credit there. Okay. Oh, I got a STEM flyer. Right, so there's this club going on. Looks like after school on Mondays and Mr. Doman's room. So here's that. There you go. Okay. Okay, so you guys know yesterday I gave you guys this projectile page. Does anybody not have this projectile page? Everybody has this projectile page, I think, from yesterday. Right? All right, so we're going to do as many of these in class as we can today. Now, as a warm-up, and I do have one Paul Hewitt video for you guys. And of course, you guys are in AC, so don't worry about anything that's mistaken. All right. So Paul Hewitt. Paul Hewitt.
There's a little device here that will shoot a projectile. A little spring here. I'm going to compress the spring. And when I do that, I can put a projectile here and watch this gang, little spring gun. Out it goes. No surprise. But I've got another ball that I can put on the end here like this. And when I go like this, it falls essentially straight down. A little bit out, okay? But kind of downish. This one goes outish. Now I'm going to do them both at the same time. When I do them both at the same time, you guys got to figure out, hey, which one going to hit the ground first? The one that just dropped down or the one that just goes out?
Ooh. All right, so you guys caught that question? All right, recap the premise here. He's got this interesting contraption. He's going to have a couple of balls, a couple of bearings, right? One on the left side and one on the right side. Right, he's going to release some spring, and then the one on the left side, I'll call it our left, so the left side, is going to pretty much just fall straight down. Hit the tabletop right here. Okay? The one on our right side is going to be fired straight up horizontally. But then, since gravity's pulling, it's going to fall into, what shape path does it make? Parabola. Aha, parabola. Want to make a parabola shape? And then maybe hit this tabletop way off screen to the right, somewhere right there. Right. But which one hits the tabletop first? Here's your options. Does the one that falls straight down hit the tabletop first? Does the one shot straight out horizontally hit the tabletop first? Or maybe do they hit the tabletop at the same time? Show of hands. How many of you guys think the one that goes straight down hits the tabletop first? How many of you guys think the one that goes straight out hits the tabletop first? How many of you guys think they hit the tabletop at the same time? Say, oh, look at I think everybody got it. Everybody got it. I think everybody got it. All right. Right. How'd you guys know? Yeah. Yeah, this gray tray right here. Hang on, I'll be right over there.
Goes out. A lot of people think, oh, the one that's fired out is going to be in the air for a longer time. You know why? The gravity going to start to pull it and say, oh, I didn't know you were moving. Go ahead. And gravity not going to pull so hard. What do you guys think? Let's try it. I tell you what. If you hear this, all A's, all for this course, all A. Registrar say, Hewitt, my God, Hewitt, you got all A's in your class. I'll say, I had a sharp class, honey. I had a sharp class, all right? All A's. But if you hear this, then you gotta do your homework. Okay? Here we go again. Here we go. This next moment may be very important for a lot of you who of your everything riding in your grade. All right, here we go. Here we go. Listen. What do you hear? How many heard this?
Okay, so you guys, yeah, they did hit the tabletop at the same time, exactly like you guys said they would. I do have, got this right here. I bet all of you remember from yesterday. All of you remember this. That if you fire a projectile straight out horizontally, it has zero initial vertical component of velocity. Of course, that changes as gravity's pulling it, but initially it's zero. Same as if you just dropped it. So if you drop something and fire something horizontally at the same time, yeah, they do hit the ground at the same time. They take the same time to reach the ground. Yeah. Okay. Okay. Actually, this is a good picture right here because the first one that we're going to solve together in class does look just like this. I have a cannon on a cliff firing horizontally. Okay. So all these three scenarios on the left side of the page are that category question. They all say there's cannon on a cliff firing horizontally. That's for these three. Okay, you guys got those three? You can use this as a picture for the left three. Now, the three on the right side has a little bit different scenario. They are all some category of this picture, where you have a cannon on a large plane and you fire at some angle. You have it ramp at some angle. It goes into a parabola shape and lands somewhere way downfield. Okay. That's these three on the right. And we'll do at least one of these today. Right. And then we'll see what we have time for after. I'm going to do this scenario and this scenario with you guys, the ones that got started right here, and then we'll see how much time we have left. Okay. On the back side of this page, there are three scenarios where, it's kind of a hybrid. Yes, there's a cliff, cannon on top of a cliff, and also it's ramped up at some angle. Now, one scenario, I'm really helping you guys out, so I'm walking through step by step. First do this, then do this, then do this, right? You'll know exactly if you're getting them right. Okay. These on the right are a little bit more open-ended, although they're the same premise. So I'll see if you guys get those two. All right. So you guys know what we're doing. Big picture roadmap. All right. So first one we're doing together. We're doing this scenario that's marked number 5 through 8. You guys see number 5 through 8? Okay, 5 through 8. So a cannon fires a cannonball horizontally off a cliff at given speed from the edge of the cliff of given height. So this one I happen to be giving you the cliff height, right? And I'll give you the firing speed of the cannon. So you happen to have that for 5 through 8. Find all these questions. So there's a whole bunch of questions I have tagged to this. How much time does it take for the cannonball to reach the ground? That's to go from here to here. How much time? Okay. How far does the cannonball land from the base of the cliff? Could that be this horizontal displacement that I have marked in green on this poster? Okay. How far from the base of the cliff? Okay. And there's a couple of questions at the end that go together, 7 and 8. Something about vertical component of velocity, okay, and then horizontal component, and you can put that together and get the total crash speed. How fast is the cannonball crashing into the ground right at the end? So I'm going to draw this on paper and mark what I know, and then see how it solves from here. So this is number 5 through 8. So we got 5 through 8. Cannon on a cliff. So get a cliff going. Got a little cannon up here at the top. A blasted cannonball. I'll call this V blast. Okay, it's like the blasted cannon. Okay. By the way, next week, I'm going to take you guys out to the balcony. I got little launchers with little squishy bouncy balls, and you'll have the exact same setup. Pew, pew, pew. And this is going to follow a... what shape is this again? Parabola path. Yeah, parabola. Land somewhere down there. So I told you the height of the cliff. You guys know I make like 10 different versions of this paper, right? So my numbers are almost certainly different than yours, unless you're really, really lucky today. But how I organize this information in these tables, you see there's like a 5-column table, and then there's also a 3-column table. Right? The 5-column refers to any vertical information I put there, and the 3-column refers to any horizontal information. Of course, there's more vertical information because, guys, which way does gravity pull? Down. Yeah, down, which is along the vertical axis. Gravity pulls straight down. Right? So there's going to be an acceleration, which means velocity is changing. Yeah, so there's a lot more going on vertical. Horizontal, it's more straightforward. There's only one horizontal equation, which is x equals vt. Distance equals v times time horizontally. Right? Guys, is there any acceleration horizontally? No. Well, not after the cannonball's blasted. It's just ghosting. Okay. Now, all these values are vector values. That's to say that there's a direction, a spatial direction, except for one. Because what's the only variable that we're working with that is a scalar value, does not have a spatial direction? Time. Okay. Therefore, does it take the same time to go from here to here, regardless of if you analyze it vertically or horizontally, same time? Yeah. So that's the one variable that you're allowed to transfer from one part of the table to the other part of the table. Okay. I'm giving you guys little tricks, like organizing tricks. Way to see the big picture. Okay. You guys know if you open up a physics textbook, they're not going to give you these very convenient tables, right? They'll give you something more like this question on the back, where I just print some information like that. You got to figure out everything. But I'm showing you guys how to organize it in your mind. Okay. Okay. So mark what I know here. I know this height is on my paper it says 13 meters, and on your paper it's probably something different. You guys locate your clip height. I know gravity is now this paper says to use 9.8 meters per second squared, and this would be downward, of course. Okay. So I'll go ahead and use that just so that I get exactly a multiple choice answer. Right? There's no question of like around a 10, does it make it that? There's what else did I tell you? Oh, I told you the blast speed. Okay. Guys, is the blast speed the same thing as the horizontal component of velocity all the way down to the ground? Is the cannonball going across the field that speed? All the way across? Yeah. Now the overall speed is speeding up because it's all speeding pulled down. But if I just look horizontally, this V blast is the same thing as V sub x. They're the same thing because you're aiming the cannon horizontally. And on my paper, that says 90 meters per second. And for you, it's probably something different. Right. So you guys good with the starting information? Okay. All right. Oh. All right. First question is how much time does it take to reach the ground? After that, we'll figure out how far does it go horizontally. I'll call that x, and then we'll figure out some other things from there. Okay. So how can you solve for how much time it takes to reach the ground? And I'll narrow it down to one of two options. Should I start solving for time by focusing on the horizontal information or on the vertical information? Where should I start? Exactly. You guys see on the vertical side, I'm stacked with a bunch of vertical information. I know 3 kinematic values. That means I can definitely solve anything vertical, right? Right. Now horizontal, well, at least not at the beginning, at least, because you only know one horizontal value, which is how fast it's going across, right? But guys, after I get this time again from vertical information, can I very simply transfer that time to horizontal, and then I can solve anything horizontal? Right? You guys see how this play is working? All right. So let's do that. Let's start with the vertical. And if I'm starting with vertical, that means I'm back to these 3 amigos that involve acceleration. So let's see. I want to get time based on ball height. What's the only one of these 3 that relates some kind of displacement to some kind of time? There's only one that does it.
The middle one.
Huh? Okay, let's go bottom to top. Do you want to use the bottom one? No, because it doesn't even mention time, so you don't have time to solve for it. So that's not very helpful. Do you want to use the middle one? Well, does this say anything about here? Let's see. What would we know, not know? Let's say pick that one. Okay. Say, I see this B final equals B initial plus 18. Now let's straight off the paper. Now, if I turn this into a vertical version, this would really be V final in the y direction equals V initial in the y direction. Could I just say plus GT? Because the gravity would be the acceleration. Okay. Now, I do know that, actually, you do know this here. Because as long as you aim the cannon horizontally, then how fast is the cannonball initially moving vertically? You see it in the picture. Okay, so if I blast the cannonball horizontally, right when the cannonball is leaving the barrel, is it moving up or down at all?
No.
It is not. In which case, this number is what? 0. Goodbye. Ooh, you know gravity is 9.8 meters per second squared on this page. You know that. Okay. So times some amount of time t would give you the final velocity in the y direction, or that component. Do we know either one of these yet? No. So we kind of hit a dead end. Now I'm going to hold on to this because I think this is about to be useful in a few minutes, but it isn't right now. We hit a dead end. So I'll put that to the side. And let's keep it. Well, I guess there's only one equation left. Is that the top one right here? Okay, let's try that one. So straight off the page says some displacement equals initial velocity times time plus 1/2 acceleration times squared. That's straight from the page. Okay. So let's modify that for the scenario. Is this displacement? If I want to make a vertical type equation, am I talking about this height change right here? It's height change. So I'm going to call this h. You could also call it y, h or y. Okay, like a vertical height change. Okay. Equals this is v initial in the y direction times t plus 1/2 g t squared. So that's how that all connects like that. Now, for this particular scenario, I'm going to define down as the positive direction. That way, I only ever have positive numbers. You see, to the right can be positive in the horizontal, and down can be positive in the vertical, and everything's only ever going to be positive. I'm not working with any negatives on this one. Okay, that'll change later today, but not for this one. Okay, is that okay? We're doing. Right. So, I know this is 0 again. Goodbye. It's gone. That's just 0. Okay. Which means here, I'm going to solve this two ways. Two ways I'll solve this. Okay. I'll solve this in terms of variables, and I'll solve this with numerical values. Okay. Of course, it'll be the same thing either way. Okay. I just want to show you guys in principle you can do this. H equals 1/2 gt squared is what this is boiled down to. Or if I plug the numbers in, see, I have a height of 13 meters equals 1/2. And then in place of g, I'll put 9.8 meters per second squared. And then solve for t, which is b squared. Okay? You guys see, that's really the same thing though, right? Actually, in terms of variables on the left, that could solve all y'all's papers. And there's one on the right, I want to solve mine. I said. Oh, okay. Yeah, the 13 meters comes off my paper. So see, I have a cliff height of 13 meters. Okay, that's to say that the ball is going to move. Okay, and I got it right here. Actually, it's labeled Y for the cliff height. Yeah, okay. Like a vertical displacement. Okay, so the vertical displacement is the height of the cliff because we're going from the top of the cliff down to the valley below.
So why is it this paper? I left all mine at my house. So
okay. Yeah, so that's a good question.
equals y is h.
Yeah. So maybe I should have called that Y, but yeah, same idea. Okay. So vertical height change. Okay. All right. So what do we do here? Can you guys solve for t? Solve for t? Okay, so I'll do it. You guys do it. Let's see if we're getting correct values here. So 2h on g is t squared. So t is the square root of g. We're over here. 13 meters. 2.8 fucking squared plus t squared. Okay. So t equals the square root of 2, 13, 98 number of seconds. Yeah, let's see, what would that be? Okay. I'm getting a false time of 1.63 seconds. Okay, let's take my false time. Does that show up on my page? I hope it does. Let's see. Oh, yeah. That is definitely an answer choice. Good. All right, so that worked.
Wait, how's it 2 times? Where is it?
Where did I get what from? Huh? Okay. So, guys, we're starting off with h is 1/2 gt squared, right? Okay. Now, you need to cross multiply the 2 to get 2 times the fall height. So 2 times the fall height. Okay. And then divide down the gravity field g. Okay. Okay. And now that's t squared. So the last step is to take the square root.
Is h?
Guys, h is the height of the cliff, which is also it's labeled y on the paper. Okay. It's like a vertical displacement. Okay, so the vertical displacement is the height of the cliff. Okay. Going from the top to the bottom of the cliff. Okay. So the cannonball moves this many meters vertically. Now your paper probably has a different cliff height, but that's where you find it though.
Wait, so the y is the
y is the vertical displacement, which is the height of the cliff. Remember how my cliff was 13 meters tall? Do you see how tall your cliff is? Okay. Your cliff height is whatever number is in this box right here. Mine says 13 meters.
So what?
G,
Oh, it's not.
yeah, it's 9.8 meters per second squared. Yeah, that's the same thing as like the vertical acceleration. Right, vertical acceleration could be G. Okay. Yeah. So yeah, here it is variables. Here it is with the numbers plugged in. You only have to do it one way. You don't have to do it both ways. I'm just showing you both ways. Okay. No matter how you do it, you get the same thing. So it ends up being 2 times. So the square root of 2 times the drop height divided by the gravity field. That's all underneath the square root. Right? That'll tell you exactly how much time it takes to fall that height. Which of course is the same as if you just drop the ball off the edge of the cliff. Actually, you know what? I think some of you guys might be looking at what I just did right here and saying, wait a minute, that looks really familiar. Where does that look familiar to?
What we did yesterday.
Reaction time. What we did yesterday. It's the same thing. That's what you did yesterday. That's the same thing. Yeah. That's how much time it takes to fall some height. That's it. Same thing. Same thing. Same thing. Hey, you guys good? You guys good? All right, ready for our next part? Okay. So now you know the time. In fact, if you want to, you could write the time in seconds in that little box right there. It should be whatever the answer to number 5 was. Okay, let's got that. Okay, next question says, how far has the cannonball landed from the base of the cliff? That's this X right here. So we're going to go solve for X. How far from the base of the cliff? Sometimes it's labeled D. Today it's labeled X. Whatever. You label it. Okay. Now, since this is a horizontal question, right? Horizontal displacement, horizontal question. Guys, in projectiles, there's only one horizontal equation. What's the only horizontal equation in projectiles? X equals what? Yeah, vt. V sub x times t. Right, that's it. Right. There's no acceleration horizontally. Right. If you look really close, it's actually on this page, sort of in disguise. Because if I set all these a's equal to 0, because we're talking about horizontally, gravity does not hold horizontally, so all these a's are 0. Right. Right. Okay, so the speed is always the same horizontally. That's true. Right. And up here, this term goes away, and you got, and my computer's lagging. Here we go. X equals vt. That's it. That's it. As long as we're talking strictly horizontally, right? Strictly horizontally. Sure. So let's put this together then. So how far the cannonball lands from the base of the cliff is how fast it was going. Now for me, that's 90 meters per second. Because that was my blast speed, horizontal. Times how much time, which I just found right here, is this many seconds. Right? Sure. So let's see, how far then equals.
Did we just round up?
Yeah, you have to round at some point, right? So mine's at 146 point something. Yeah, that rounds to 147 meters. Okay. I guess you should round to the nearest meter. So that's all I could fit on the page. Nearest meter. I mean, it probably makes sense anyway. Nearest meter. Yeah, I see an answer choice right here. Okay, sorry for the lag. There it is. I see it right here on my paper. Is exactly what I got there. Is this working out for you guys too? Are you guys getting answers on the page? Is this working for you guys? Everybody's good? Everybody's good? All right. All right. Okay. Now, the next 2 questions go together. They have to do with this crash down here. So it's lost track on the ground. So I need to draw this crash vector. It's going to go like this. Now, I'm going to hold my ruler flush to this parabola curve. You guys remember this is a dash parabola, right? And right at the very top, you guys see how my ruler is being held horizontal? Right, horizontal? Because the cannon is aimed straight horizontal, and the cannonball moves horizontally for the first and a second. Right. Then, as the ball falls, see how my ruler is turning? Like right now, the direction of the cannonball motion is that way. Okay. And then it gets steeper, 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 until bam! It hits the ground right there. You see how my ruler is aimed, well, the steepest it's been so far? Right? So I'm going to draw a line flush to the curve right here. I think the math term is called a tangent line, like that. Okay. And I'll label this V crash. Right. That would be the crash velocity right there. Crash velocity. Okay. As the cannonball is falling, do you think here if somebody points a radar gun at it get the instantaneous speed. Okay, instantaneous speed, like right there, right there, right there, and then rise is about to crash. Okay? Is the cannonball overall speeding up, slowing down, or maintaining its overall speed? What do you guys think? Speeding up. Does that make sense? Right. I know if I dropped the ball, like it would definitely be speeding up. Yeah, turns out this will be too. So the overall crash speed, I think, has to be faster than the blast speed, right? Makes sense? Right. So I'm going to take this crash speed, which is on a diagonal, and I'm going to break it into components. It's going across the field, and it's also coming down. Still crossing down. Okay, you guys got the same thing in your notes? Okay. I'm going to label these components. Guys, what should I label this component right here?
Yeah.
B sub x. Yeah. In fact, I bet you guys know what Vx is. What is that? Yeah, it's the same as the blast speed. Yeah, it's the same. That never changed. Right? Going across the field, it never changes its speed going across the field. It only changes its speed like vertically and overall, of course. Right? Right? Like if you're up in a hot air balloon, way up in the sky, watch this cannonball go across the field. It looks pretty much constant speed all the way across. Right? That's all you see. Now, how about coming down? Can I call this V final in the y direction? No, in the y direction, it's a little trickier because it's always changing. But V final in the y direction. Okay. What do you guys think we're going to do next? Okay, eventually. But before that, we gotta. Does number 7 say solve for VF in the y direction? What's the vertical component of crash speed? Crash velocity. Right. And to do that, okay, so we're looking at something to do with velocity. Something to do with velocity. What do you guys feel like? First, second, or third? 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 Okay. Do it. We've got an option here. So just don't pick the first one, because the first one doesn't say anything about final velocity. But both of these have final velocity. The second one will get it as a function of fall time. And the third one gets it as a function of the cliff height. And I'll show you guys that both of these tell the same correct answer. Okay, you guys want to see it? Okay, let's do it. Okay, so you can pick the second or the third, and I'll do both to show you that it all works out. Okay. So I could pick V final in the y direction equals V initial in the y direction plus GT. That's sort of a modified version of the second one. Or I could go V final in the y direction squared equals V initial in the y direction squared plus 2GH. Isn't that like 2AX? Right? 2GH. Same idea. Right. So here, I'll just go ahead and plug numbers in. Because what is this right here? 0. 0 meters per second. Because initially in vertical in the y direction. So this one's also 0. Why? Okay. We're solving for VF in the y direction. Right. Okay, so this one actually there's just one algebra step. Isn't it just you're always just going to take the square root of 2GH, like in terms of the cliff height. But in terms of time, you just do G times T. So let's plug this in. So final velocity in the y direction is, I got 9.8 meters per second squared times, my fall time was, remember, mine was 1.63 seconds. That goes right here, 1.63 seconds. Okay. Okay. Or alternatively, in terms of cliff height, it should be the square root of 2 times gravity is 9.8 meters per second squared. And my cliff height was 13 meters. Is this and this? They have to be the same thing? You're gonna see. We're gonna put physics to the test. 9.8 times 1.63. So BFY equals 15.97. I'm going to round that to 16.0 meters per second. Oh, I should have asked you guys 16 what? But you guys would have said meters per second because we're talking about a velocity. Yeah. Okay. Okay, so it should be 16 meters per second. What about the cliff height version?
Yeah, that's good.
So final velocity in the y direction. Keep in mind, this is only in the y direction. So what's the square root of 2 times 9.8 times 13? Okay. Guys, when I hit enter, my calculator better say what? 16? Oh, yeah. Oh, yeah. 16 meters per second. It's the same thing. There's more than one way to get that. And is that a choice on my paper?
No, they're not.
Oh, yeah. Oh, yeah. I'm seeing it right there. Oh, yeah. Okay, how about you guys? Is that working for you guys too? Yeah, working out. Yes. Here, maybe maybe in class.
Wait.
Here, take what? Yes.
Where did you get the, like, the square?
Where to go? What?
Like, yeah.
Oh, square root. Okay, because
That's
okay,
the third option.
yeah. So right.
Yeah.
So solve two ways. You can solve this based on drop time or on the height of the cliff. Now, the height of the cliff, you work through this one right here. Okay. This initial velocity in the y direction is 0, so that goes away. The height of the cliff, you plug in for x. Okay. And then this final velocity, you still have to take the square root.
Oh, wait, so you're just like using that equation?
Yeah. Yeah, I'm just using this right here. This is this. It's the same thing.
Oh. Okay.
Yeah. Yeah. Okay. Alright. Alright, so we gotta finish this up though. So now I know that this is 16 meters per second. Okay. Finally. How do you get crash speed? Pythagorean theorem. There you go. It's the square root of a squared plus b squared. So 90 squared plus 16 squared, and then square root, this would be meters per second. Okay. So what's the square root of 90 squared plus 16 squared is 91.4 meters per second. There it is.
Yeah.
Okay. And then that is the answer to number 8. That's number 8 right there. Okay. Pythagorean theorem. Can you guys do Pythagorean theorem? Get number 8. Okay. Okay. Oh, I have a bonus question for you guys. Guys, what is this angle? I'll call this theta. How do you solve that theta right there? Inverse tan of 90 over 16. Could you do that?
Yeah.
Okay. The meters per second. Cancel. Inverse tan, 90 on 16. I'll say that's 80 degrees from the vertical. There you go. So actually my picture's not really to scale. It's actually skipping and pretty horizontal-ish. Guys good? Okay, so there's one more want to look at today. Help you guys out with. Let's look at number 18 through 20. You guys see a cannonball is boston at a castle wall. Right? So I told you how high up the castle wall the cannonball in. Notice it turns gravity negative because if you're blasting a cannonball kind of upish, and gravity's pulling downish, you need direction. I didn't tell you how much time, and I told you how far away the castle wall is from the cannon. So I'm going to draw that picture and get as far as I can here. We'll raise it up the clock, but do as good as we can here. So got the ground. I got castle wall over here, and here's my cannon. Turned up at some angle. Now I did not tell you the angle. That's one of the questions. Wow. Got blast. I'll call this V blast. Okay. And that's another question. How fast the cannon firing? This guy hit the castle wall right here, and this vertical displacement I'm going to call Y. Okay, so the cannon starts on the ground, and the cannonball lands some vertical displacement Y up the castle wall. Okay. What do you know? Okay. I told you the height of the castle wall. So mine says 15 meters. Yours probably says something different. I told you this distance right here, X, to the castle wall. I told you that. On my paper, it's 300 meters, and for you guys, it's probably something different. And I told you the time. For me, it's 5 seconds. For you, it's probably something different. And I also told you the gravity field. I gave it as negative, so that when you blast the cannonball kind of upish, gravity's pulling down. That's what's going to make it bend back down. Okay. Now, here, I'm going to go a little fast on this because I want to fit in some stuff before the time runs out. Okay. Do you guys see this angle theta right here? That's one of the questions. What's this angle theta? When you see a question like this, one of the first things you always do is break the blast velocity into components. So this could be v blast time. Guys, this component down here is v blast times what? Cosine theta. And that is v sub x. Okay. And this component right here, which I'll call v initial in the y direction, that's v blast times what?
Fine.
Sine theta. Yeah, sine theta. Okay. Now to solve this, here, big picture here. If you need to go home and watch this video and think about this a little deeper, right? Is there's going to be a vertical aspect and a horizontal aspect to this question. So the horizontal is pretty straightforward because there's only one horizontal equation: x equals v sub x times t. Okay. In this case, x equals v blast times cosine theta times the time. Okay. I told you the x and I told you the t, so you have those values. Now in the vertical direction, so vertical, I have I do this: y equals v naught y t minus 1/2 g t squared. That's the first kinematic equation. I gave you one more thing. So v naught y is really v blast sine theta. Okay, and then I can have a t times t. Okay. Then minus 1/2 gt squared. Okay. Now you know y, check. You know v you know t, check, and you know g, check, gravity field. Okay. So you don't know v blast, and you also don't know this theta. Okay. All right. But guys, big picture here. If you don't know v blast and you also don't know theta, that's two unknowns, right? Two unknowns. Okay. But you have two independent equations. Can you solve two unknowns with two independent equations? Right. Here on out, you just have to know how to do the algebra. Okay. That's all I have time for, so I'll hang that up there. But we will do more of these next week.